Okay, so let's get into understanding gases. And I need to pull up the chat so that I can see everything that's going on there. Okie dokie. So what you have in front of you is just an empty chamber at this time. This chamber has several things that it allows me to do. Number one, I can change the volume of the chamber by simply moving the handles. Number two, you'll see that the chamber does have a temperature gauge. And at the bottom of the screen, you'll see a bucket that says hot and cold. This bucket will allow me to actually alter the temperature. Also on this, you will see a pressure gauge. We will be looking at all of these aspects throughout the first portion of this lab. And then finally, you're going to see a bicycle pump. And through this bicycle pump, I can add two different gases. I can add the purple gas and I can add the red gas. And at times I'll be adding both gases together. So this is just a really nice interactive that allows you hopefully to come up with the kinetic molecular theory and several of the concepts associated with gas laws on your own. I think it's a nice way to do that. So let's get started. Let's add a little bit of gas. And we're going to give it a second. Okay. So at this time, I would like you to put in the chat some of the things that you see. Okay, so one of the first things you noticed is that the particles definitely spread out. Gases are going to expand to fill whatever volume is available to them. So the volume of a gas is equivalent to the volume of the container of that gas. Now, yes, the temperature did increase, but it pretty much is holding steady at this point. But somebody did make, or a couple of somebodies did make a comment that the pressure is fluctuating. So I agree the pressure is fluctuating. Now let's think about why the pressure is fluctuating. The pressure fluctuates because the pressure is related to the number of gas molecules that encounter the side of the chamber. So there's going to be times where there's very few molecules encountering the side of the chamber, and other times there's a greater number. The greater the number of molecules encountering the side of the chamber, the greater the pressure is going to be. Now, one of the other things, let's see, trying to look at what you gave me. Okay, so a comment was made that the gases are bouncing around. So basically, a gas is going to move in a straight line until it encounters an object, and then it is going to move in a different trajectory. Now, and that is going to be true. Now, let me ask you a question. Does anything happen to the little purple balls when they encounter each other? They bounce off of each other. They change their trajectory. They do seem to slow down. All of that is perfectly valid. So they bounce off of each other. What you are observing is what is considered to be an ideal gas. An ideal gas, when we're discussing an ideal gas, what it means is that the collisions are elastic. Therefore, no reaction actually occurs when the two molecules collide. Now, I will agree that at least temporarily, the molecules do change their energy. They tend to slow down. And that is due to the fact that the molecules themselves have passed on some of their energy to the molecule they collided into. And so we do see it slow down, and then over time it would pick back up. So those are all important aspects. So let me just summarize the key points to this. The very first one was that gases will spread out to fill whatever container is available to them. Gas molecules move in a straight line until they encounter an object. And when they do so, their trajectory changes. When they do encounter an object, they apply pressure, thereby transferring some of their energy to that object. When that object is the wall of the container, the pressure is fluctuating, as observed by our pressure gauge. One thing that did not get mentioned is that the molecules themselves are very small compared to the space between them. So that's another piece to this puzzle. Okay. So what I want you to do now is I am going to adjust the volume, and I want you to pay attention to how the adjustment of the volume impacts the pressure. What observation can you state? The volume increased and the pressure decreased. In other words, pressure and volume are inversely related. And the main reason that the pressure did increase is because the molecules have a further distance to travel before they encounter the object or the walls of the container. Okay, let me start this over with a fresh batch. Give it a moment. Okay, now we're going to actually play with the temperature. We're going to heat up this temperature or heat up this container. What are some of the things that you noticed? Okay, so y'all caught most everything that I was looking for. One of the first things I was looking for is the fact that, yes, the kinetic again, we're talking about kinetic molecular theory. And if you'll recall, kinetic means energy of motion. So these gas molecules' motion increased with an increase in temperature, meaning that there is a direct relationship between the temperature and the kinetic energy, which makes perfect sense that would be the case. The second thing that was made note of is that the pressure increased with increasing temperature. And again, if we understand kinetic motion, if we understand these gas molecules, that makes sense, because as we increase the temperature of our gases, they're moving faster. If they're moving faster, then when they collide with the walls of the chamber, then they're going to apply a greater amount of pressure than they would otherwise. So pressure is directly related to temperature. Kinetic energy is directly related to temperature. And as somebody pointed out, basically that pressure kept going until the lid blew. So, and then what did we see? We saw the gases spread out because now they had a greater volume. What is not obvious is the relationship between volume and temperature. In this particular interactive, we are dealing with a rigid container. But let's say we had an elastic container, a lot like a balloon. Then when you heat the gases within the balloon, what would be observed is that the balloon is going to expand, because volume and temperature are also directly related. Now, this next piece may seem obvious because we have some of what we just said. But again, I want us to see this relationship between temperature and motion or kinetic energy. But this time I'm going to cool it down. And we cooled it down until it hit 0 Kelvin. And what have we noticed? The pressure decreased to 0 at this point. And the molecules, if they are moving, it doesn't appear that way. That is why the Kelvin scale is considered to be the absolute temperature scale, because at 0 Kelvin, all kinetic motion stops. So our gas molecules have completely stopped because we hit 0 Kelvin. Okay, let's see. I'm going to reset this thing. And we're going to pump in some more purple. But this time I'm going to also pump in some red. At this point, don't worry about the pressure. What I want you to tell me is what can you say about the purple versus the red? Okay, between everybody, there is definitely, y'all definitely have it. Basically, the size of the atom also impacts the kinetic energy. The less mass that the atom has, the faster it's going to move. So the red, which is the smaller molecule or the molecule with the less mass, moves much more rapidly than the purple molecule or the molecule with the greatest mass. Now, let me reset one more time. And let me get the purple up to speed. Takes a little bit. Okay. And we're currently at a pressure around 6.0-ish. I know it fluctuates. Now let me add in, and if we were to count it, let's see, is there a, there's currently 50 purple particles in here. Now let me get the red in. We're going to put in 50 red particles. What did you notice about the pressure? The pressure doubled when we doubled the number of gases. That means that if I were to add another 50, it should be triple. Now let me ask a question though. Did the volume of the container change or did the temperature change? No. The only thing that changed was the amount of particles. And the pressure changed because of the amount of particles. All of these things are going to come into play when we start talking about the gas laws. But hopefully now, as we talk about these gas laws, you can better picture the kinetic molecular theory, and you can better picture what's going on when we talk about these gas laws. Okay, so I am going to stop share there. And I am going to start share on my iPad. And I want to make sure I can see chat. Okay, so gas laws. Basically, there are 4 variables that we used to describe our gases. The very first one was very common, and that is the pressure. When we start dealing with the gas laws, the pressure will be represented with a capital P. And there are a variety of units that you can use to describe pressure. Now, I will tend to use atmospheres, but some of the other units of pressure include millimeter mercury, inches mercury, torr, pascals, which is represented with a PA, maybe even kilopascals. And then the other one that I have listed here is PSI, which is used in tires, whether it's for a car or whether it's for a bicycle. And it stands for pounds per square inch. So when you're describing the pounds per square inch, you're literally describing the pressure of the gas inside. Now, because I do tend to use atmospheres, I have given you the conversion factors that will allow you to convert between various pressure units and atmospheres. And yes, you will receive these conversion factors on the final exam. So you don't have to memorize them. When we talk about the gas laws, the unit of a second variable is volume. What volume does it take? What volume does the gas have? The volume of the gas is going to be equivalent to its container. The units of volume, liters, milliliters, centimeters cubed, meters cubed, those are all units of volume that could be used. The third variable is the amount of gas, and we will be using moles. I mean, that's our go-to is moles. And then finally, the temperature of the gas. And folks, the only acceptable unit for temperature when you're dealing with a gas is Kelvin. That means you better be prepared to convert the degrees Celsius into Kelvin. Or if I give you a temperature in Fahrenheit, you better be prepared to get it to Kelvin, because the only acceptable unit for temperature for a gas is that of Kelvin. These are the four variables that we use to describe gases. What pressure do they exude? What volume do they take up? How much of the gas is there? And at what temperature is that gas? Now, there is another term that you do need to be familiar with as we progress, and that is you need to be familiar with the term STP. STP stands for standard temperature and pressure. And this you have to have memorized. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. In answer to Trevor's question about whether you need to memorize your temperature conversion formulas, the answer is no. They have been on every single test and they will continue to be so. But you do need to memorize the term STP. This next piece that I'm about to discuss, you will not need to be prepared to use. I do want to discuss it, but I'm not going to ask questions directly about these gas laws that I'm about to discuss. I'll tell you when. You got to know your stuff again. So gas laws. One of the examples that I did with the interactive video was I increased the volume and you saw that the pressure decreased. Therefore, volume and pressure are inversely related to one another. When the amount of the gas and the temperature of the gas are held constant. That is Boyle's law. Boyle's law says P1 V1 equals P2 V2. Boyle's law is used anytime you're working with pressure volume changes. The second one that we have here, we didn't actually get to observe because we were dealing with a rigid container. And that is that the volume and the temperature are directly related when the amount of gas and the pressure of the gas are constant. And so because I could not give you an example using the interactive, I tried to give you an example with respect to a balloon. And that is, if you take the balloon and you increase the temperature, because the balloon is elastic, it's going to expand, at least initially. Eventually it'll pop. The third gas law, you did get an opportunity to see, and that is Gay-Lussac's law. Basically, Gay-Lussac's law says that the temperature and the pressure are directly related. When I increased the temperature, we saw the molecules move much, much faster. So they had a greater amount of kinetic energy. So since they had a greater amount of kinetic energy, when they impinged upon the walls of the rigid container, they applied a greater amount of pressure. And so Gay-Lussac's law is P1 over T1 is equal to P2 over T2. Again, we use Gay-Lussac's law anytime we're dealing with pressure temperature changes, while the volume and the amount are held constant. The last law we didn't actually observe, and that is, but it's called Avogadro's law. And let's face it, the term, when we first encountered Avogadro was when we talked about Avogadro's number, which was 6.022 times 10 to the 23rd of anything is equal to 1 mole. So Avogadro's law deals with moles. Specifically, it says that the moles and volume are directly related when the pressure and the temperature are held constant. And I was not able to directly illustrate this, but I can give you one that I have a feeling most of you have experienced. And that is, let's say we're blowing up a floaty for a pool, or say we're blowing up a mattress to sleep on, a blow up mattress. So we're sitting there and we're blowing it up. And so as we add air, the volume is increasing. But we get a little winded, so we stopper it up for a minute and calm down. And then you go back and you add more air. And as you add more air, it expands further. So basically, if you'll think about that, the difference between the smaller volume and the larger volume was the amount of air that we had added to the mattress. And so you can say that the volume is directly related to the amount of gas. There is one that I have not written on here that you also will not be using, and that is the combined gas law. The combined gas law basically combines Boyle's law with Charles' law. And it is used anytime you're talking about a pressure, volume, temperature change that can occur on the gas. But starting with this next section, we go back to the things that you have to know for your exam. And the first of those things is the ideal gas law. The ideal gas law takes into account all 4 variables of the gas. Takes into account the pressure, the volume, the temperature, and the amount of gas. The ideal gas law also includes the variable R, and R is known as the ideal gas constant. The ideal gas constant that you will receive on an exam is 0.0821 atmosphere liters per mole Kelvin. Now, there are other ideal gas constants. The other ideal gas constants arise from converting the pressure unit of atmospheres to a different pressure unit, such as millimeters of mercury. Or the other ideal gas constants can arise when you convert the pressure unit and the volume unit to a different set of units. Now, again, I'm only going to be giving you R is 0.0821 atmosphere liters per mole Kelvin on the exam. Now, when we start talking about ideal gas constants, I often refer to them as dictators because they literally dictate the units for everybody. According to the ideal gas constant I will give you, the pressure unit better be in atmospheres. The volume unit must be in liters. The amount of gas in moles and the temperature of the gas in Kelvin. So ideal gas constants are dictators. They tell you what the unit should be for everybody else. Now, working ideal gas law problems, I mean, you don't have to follow the method that I will be using. But in general, the way that I work through this is I start by making a list of the information that I was given. Making the list of the information given helps me to determine the gas law I'm going to need. Once I know the gas law that I'm going to need, it allows me to identify any missing pieces of information. So basically, I start by making this list so that I can identify the gas law that I want to use. Once I've identified the gas law that I want to use and all of the pieces of information that I need, I then go through and make all my units match up. So my pressure, I will make it into atmospheres so that it matches up with the ideal gas constant. The third thing I do is I go ahead and rearrange the equation before I add numerical values. I tend to find it easier to rearrange 4 or 5 letters than it is to rearrange numbers and units. So I just see that it's easier to do it that way. So I always rearrange the equation. Once the equation has been rearranged, I plug and chug the variables that I have into the equation. And then the last step, and this step is important. It is typically the most overlooked step in the process. And that is when I finish my calculation, I make sure to look back at the question and say, did I actually answer the question? Because you want to make sure that you answered the question and you got the units that it asked for. So now what we're going to do is we're actually going to work some problems. So let's just start off with this first problem. What is the temperature of 0.52 moles of gas at a pressure of 1.3 atmospheres and a volume of 11.8 liters? So I've been asked to solve for the temperature. of 0.52 moles of gas at a pressure of 1.3 atmospheres and a volume of 11.8 liters. By making my list, I see that I have a P, V, N, and T, which means that the gas law I need is PVNRT, or PV equals nRT. Now, to use PV equals nRT, I'm also going to need an R, which again, I'm going to grab the 0.0821 atmosphere liters per mole Kelvin. At this point, I'm checking, does all of my units match up? Okay. So my pressure has to be in atmospheres, my volume in liters, my amount in moles, and the temperature, it'll be in Kelvin. So yes, all my units match. Since all my units are matching, I'm going to rearrange this equation to solve for temperature by dividing both sides through by the amount of gas in R. So PV over NR is equal to T. And then it should be a plug and chug affair. So 1.3 atmospheres times a volume of 11.8 liters divided by 0.0821 atmosphere liters per mole Kelvin times a temperature, times N, which is 0.52 moles. And that will give me my temperature. Which comes out to be 359.3 Kelvin, which if we're keeping up with significant digits, I would round to 360 Kelvin. Okay. So now let's look at another problem. Consider the reaction of carbon monoxide gas plus 2 hydrogen gases going to form methanol. What volume of hydrogen in liters at 748 millimeters of mercury and 86 degrees Celsius is required to synthesize 25.8 grams of methanol? So I start by making my list. I've been asked to solve for the volume in liters for hydrogen. I was given a pressure of 748 millimeters of mercury. I was given a temperature of 86 degrees Celsius. And I was told that I had 25.8 grams of methanol. Now, one thing to note is that the ideal gas law equation is associated with a single gas. It's important to know that because if I want the information on hydrogen, then I need the pressure of the hydrogen. I need the temperature of the hydrogen. I need the moles of the hydrogen. I need everything to be about the hydrogen. Now, the pressure and the temperature is going to be constant in this particular case because this reaction's taking place in a single container. But we need to be able to get to the moles of hydrogen in order to be able to use our ideal gas law. And the way we get to the moles of hydrogen is through stoichiometry. The molar mass of methanol is 32.042 grams of methanol, is 1 mole of methanol. And according to our balanced chemical equation, for every 1 mole of methanol that's formed, you need 2 moles of hydrogen. So in other words, we have 1.61 moles of hydrogen that is associated with this reaction if we want to form 25.8 grams of methanol. So thinking about our equation, we have P, V, N, T. So we will be using PV equals nRT. To be able to use that, we're going to need our R value, which is going to equal 0.0821 atmosphere liters per mole Kelvin. Now we need to make sure all of our units are matching. And what we quickly observe is that they are not matching. We need atmospheres and we do not have atmospheres. So we're going to need to convert our millimeters of mercury to atmospheres using the fact that 760 millimeters of mercury is equal to 1 atmosphere. So in other words, we actually have 0.984 atmospheres. Again, I will be giving you the conversion units. The second thing, our volume needs to be in liters. Well, that's not an issue. That's what we've been asked to solve for. The third thing is our amount needs to be in moles. Well, we have moles now. And the last thing is our temperature needs to be in Kelvin. And currently our temperature is not in Kelvin. So we need to add 273.15 to that temperature to get it into Kelvin. So it's going to be 359.15 Kelvin. We've identified our equation. We've made all our units match. Now to rearrange this equation to solve for volume. So we're going to divide both sides through by the pressure. And so you have volume is equal to nRT over P. Now we can plug and chug. And so we have the volume is equal to the amount of gas, so 1.61 moles times R, 0.0821 atmosphere liters per mole Kelvin times temperature, which is 359.15 Kelvin, divided by our pressure, which is 0.984 atmospheres. So you would get a volume of 48 liters. So yes, we had to do stoichiometry to find the number of moles for this problem because an ideal gas law equation has to be associated with a single gas. So if we wanted the volume of hydrogen, we needed the pressure of hydrogen, we needed the temperature of hydrogen, and we needed the moles of hydrogen. So yes, we had to use stoichiometry to get to the moles of hydrogen. Okay. I want you to put in the, let's see, how many digits would you suggest rounding to in intermediate steps to avoid errors? Normally I keep 2 or 3 over and above what I need, but your error is not going to be dramatic. And other than the questions dealing with, other than the questions on an exam dealing that will be on the final where I specifically state sig figs, I'm not too worried about sig figs. But usually I keep 2 or 3 over and above what I need, and that's plenty. Okay, I want you to put in the chat how you would answer, how you would go about. I don't want the answer per se. I just want you to go about the process and tell me how you'd go about the process to answer the next question. Okay, so when I say the next question, I'm talking this question that's on the screen. How would I solve the question that I've asked for? Okay, I'm going to need the molar mass of sodium or the gram to mole ratio. Okay, use molar mass and stoichiometry to convert the grams of sodium to moles of sodium. Okay, so maybe do the problem and tell me how you do it then, how you did it. Where does the molar mass go, for instance, in the question? Denominator of the conversion factor. Okay, so basically, folks, from everything we've done so far, if you take 18.56 grams of sodium You would then use 22.99 grams of sodium is 1 mole of sodium. And you would wind up getting 0.8073 moles of sodium. So if I were to describe this, it would be the mass divided by molar mass equals moles. So if we say mass is equal to little m and molar mass is a double M, and moles, we use the same variable we've been using, N, then we would say N is equal to the mass divided by the molar mass. Well, when you take that we just developed into consideration as N, and you plug that value in for the N that is in the ideal gas law, we can create a new equation. And this new equation is PV equals the mass over the molar mass times RT. Now, I tend to like to write it more as PV is equal to MRT over molar mass, simply because it's easier to work with. But what this new equation allows us to solve for is it allows us to solve for pressure, volume, temperature, but it also allows us to solve for the mass of the gas or even the molar mass of the gas. And if we can solve for the molar mass of the gas, then we can actually identify what the gas is. So it opens up a variety of more questions we could actually use. But we can even go further than that, because we can take this equation and rearrange it to solve for the density. If you'll recall, density is mass over volume. So taking this equation, we can start by multiplying both sides through by our molar mass. And you get PV times the molar mass is equal to the mass times RT. We can then divide both sides through by RT so that they cancel out on the right-hand side. And you get pressure times volume times the molar mass over RT is equal to the mass. Then we can take both sides and divide through by the volume, where the volume on the left-hand side will cancel out, and you're left with mass over the volume on the right-hand side. So P times the molar mass over RT is equal to M over V. And since M over V is equal to the density, then we can say that the density of the gas is the pressure times its molar mass over RT. Yes, you'll get these equations. Don't worry. You're going to get your equations. So let's look at an example. What volume in liters will 33.6 grams of neon occupy at STP? So I've been asked to solve for the volume in liters for a gas that has a mass of 33.6 grams at STP. T is 0 degrees Celsius. P is 1 atmosphere. And that's the information that I've been given. Now, folks, anytime I see a mass, I'm going to think of one of two things. I'm either going to think of every time I see mass, I'm either going to think of this equation, or I'm going to think I'm going to have to do some stoichiometry. One of the two. In this case, it's that equation. So it'd be PV is equal to MRT over the molar mass. Now, in order to be able to do this, I'm going to need the molar mass for neon, which is 20.18, I think. Yes. Grams per mole. And I'm going to need my R value of 0.0821 atmosphere liters per mole Kelvin. I'm going to make all of my units match. Pressure matches, volume matches, amount of gas is fine, but I need my temperature in Kelvin. So that is 273.15 Kelvin. The next thing I'm going to do is rearrange this equation to solve for volume. To do so, I'm going to divide both sides through by the, Going to divide both sides through by pressure. So you get volume is equal to the mass times RT over the pressure times the molar mass. Because I've already taken care of making all my units match, this becomes plug and chug. So that's the mass, 33.6 grams times R, 0.0821 atmosphere liters per mole Kelvin times the temperature in Kelvin of 273.15 Kelvin, all over the pressure, which was 1 atmosphere, times the molar mass, which was 20.18 grams per mole. So we key this into the calculator. And you get a value of 37.3 liters for our gas. Now I want to give you a moment to try this next one. I will remind you that density is equal to the pressure times the molar mass over RT. Yes, that's the density. And I will let you know that 760 millimeters of mercury is equal to 1 atmosphere. So I want you to take a moment to solve for this. And when you get your answer, put it in the chat. And if it helps, because you may or may not have a periodic table nearby, nitrogen is 14.01 grams per mole. Oxygen is 16.00 grams per mole. Okay, so I made my list. I had density, temperature, and I was asked to solve for pressure. Since I was working with a gas, I'm going to my gas laws. That's important to know what you want to go to. I want to go to my gas laws. So the gas law that I used was the density is pressure times the molar mass over RT. Because I needed molar mass, I calculated it for the N2O, and I also needed an R value. The R being the dictator, I made sure that all of my units, I watched all of the units that I could and made sure that they were the correct type of unit. I then rearranged this equation to solve for the pressure. So it was the density times RT over the molar mass. So I took my density of 2.85 grams per liter times R, which was 0.0821 atmosphere liters per mole Kelvin, times the temperature of 298 Kelvin. All of that was over the molar mass, which was 44.02 grams per mole. And that gave me my pressure. So when I calculated it, I originally got an answer of 1.58 atmospheres. You had to pay attention here because if you didn't pay attention, you would not have known that the unit was atmospheres. So because it is atmospheres, I go back and I look at my question. My question asked me for the pressure in millimeters of mercury. And again, the most common thing I see, or one of the most common things I see, is people don't pay attention to their units. Folks, gas laws, if you don't pay attention to your units, you will get it wrong a lot of the time. Units are essential in gas laws. You've got to pay greater attention to your units than they are just absolutely essential. So I would have basically, to get the actual answer I was asked for, I would need to convert this 1.58 atmospheres over to millimeters of mercury. And when I did so, I would have gotten 1.20 times 10 to the third millimeters of mercury. But I will definitely accept all the three answers that were given, 1204 or 1200. Pay attention to units. Don't forget them. Okay, so back in at the beginning, I did the interactive video. And one of the things that we noted was that the pressure was directly related to the purple gas plus the red gas. That is basically going to fall into Dalton's law of partial pressure. The other thing is that we noted was that they were ideal gases because they did not react. The collisions were elastic. So basically, because of that fact, Dalton's law says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. Because the gases didn't react, each gas applies its own pressure to the walls of the container. And so we could write P total is equal to the pressure of A plus the pressure of B plus the pressure of C plus the pressure of whatever else. Now in the diagram that, or in the interactive, our gases were red and our gas was a purple. And they were moving around in the container. And one of the things I tried to make note of is that the volume was a constant. It did not change. And the temperature was a constant. It did not change. So the only two things that changed were the pressure and the amount of gas. We can write an equation for our total amount of gas too. The total amount of gas was equal to gas 1 plus gas 2 plus gas 3, because again, the collisions were elastic. There was no reaction. And we can combine these concepts together to form an ideal gas law that takes into account a mixture of gases. The total pressure times the volume is going to be equal to the total moles times RT. So let's look at a problem. A gas mixture has a total pressure of 745 millimeters of mercury, and it contains 4 different gases. It contains carbon dioxide at 125 millimeters of mercury, argon gas at 214 millimeters of mercury, and oxygen gas at 187 millimeters of mercury. It also contains helium gas. The first question is, what is the partial pressure of the helium gas? Well, we're going to use this concept that P total is equal to P of the first gas plus P of the second gas plus P of the third gas plus P of the fourth gas. So using that, we can plug in the information we were given. We have 745 millimeters of mercury. That's equal to 125 millimeters of mercury, plus 214 millimeters of mercury, plus 187 millimeters of mercury, plus the pressure of our helium gas. And when you calculate out the pressure of the helium gas, you get 219 millimeters of mercury. Yes, with this particular type of problem, one of the key things is that all of the units, again, have to match. Units, units, units. I know I preach them, but they're the guiding factor here. Now we can go on and say, okay, what mass of helium gas is actually present in this mixture if the volume is 12 liters and it's at 273 Kelvin? So we want to know the mass of our helium in a volume of 12.0 liters at a temperature of 273 Kelvin. And we know the pressure is 219 millimeters of mercury. Again, anytime I see mass, my go-to equation is going to be PV is equal to mass RT over molar mass. So in order to do this, I'm going to need an R, which is 0.0821 atmosphere liters per mole Kelvin. And I'm going to need my molar mass, which for helium is 4.003 grams per mole. I make sure all of my units match, and right off the bat, I see that they don't. I've got to convert the millimeters of mercury into atmospheres by dividing by 760. And so we have 0.288 atmospheres. My volume is in liters, so that's okay. My quantity moles, and then my temperature is in Kelvin, so I'm good. Now I'm going to rearrange this equation to solve for mass, and it comes out as PV times the molar mass over RT is equal to the mass. Now I'm ready to plug all this in. So pressure is 0.288 atmospheres times the volume, which was 12.0 liters, times the molar mass of 4.003 grams per mole, divided by R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature of 273 Kelvin, and that will give me my mass. And the mass comes out to be 0.617 grams of helium. There are a variety of ways to use Dalton's law of partial pressure. This is simply one. I could have used Dalton's law of partial pressure and used stoichiometry with a reaction. I could have used, so there's a number of ways we can go about this. There is one more thing to discuss today, and that is based off of Dalton's law of partial pressures. If you'll recall, I said that the total number of moles is equal to the moles of A plus the moles of B plus the moles of C, and so on and so forth. That concept can lead to what is known as a mole fraction. Mole fraction is a unit of concentration, and you're going to need to know this unit of concentration as soon as you get into college chemistry too, nearly. I think it comes up in maybe the second chapter. Mole fraction is represented by the Greek letter chi, or an X. So if I have X of substance A, or mole fraction of substance A, that would be moles of A over my moles of solution. Where basically, folks, this moles of solution is the same thing as in total. Now, once we get mole fractions, your mole fraction of A plus your mole fraction of B plus however many is going to equal 1. So all of the mole fractions together equal the value 1. Mole fractions do not have a unit. They're just a decimal. So let's look at an example. A gas mixture contains 1.25 grams of nitrogen and 0.85 grams of oxygen in a 1.55 liter container at 18 degrees Celsius. Calculate the mole fraction of nitrogen and of oxygen. Well, the first thing we've got to do before we can calculate a mole fraction is we actually got to get to the moles of each of our substances. So we're going to take that 1.25 grams of nitrogen and convert that into moles of nitrogen, with the fact that there are 28.02 grams of nitrogen in 1 mole of nitrogen. So that comes out to be 0.0446 moles of nitrogen. We do the same thing for our oxygen. We have 0.85 grams of oxygen. 1 mole of oxygen has a mass of 32.00 grams. So that is 0.0266 moles of oxygen. So now we can get our in total, which would be our moles of solution. And that would be equal to 0.0446 plus 0.0266. Or in other words, we're talking about 0.0712 moles of solution. Now to get our mole fraction, for our mole fraction of nitrogen, that would equal the moles of nitrogen, which is 0.0446, divided by the moles of solution, which is 0.0712. Which comes out to be 0.626. And then we can get our mole fraction of oxygen. You can either calculate the mole fraction of oxygen the exact same way we just did with nitrogen, or you can remember that all of the moles fractions have to equal 1, and you can go 1 minus 0.626, and that is equal to 0.374 would be the mole fraction of our oxygen. Now, this isn't about mole fraction, but it is about the next piece, which is to calculate the pressure applied to the container by the gas combination. Because we have more than one gas, we would use P total. V is equal to N total RT. We were asked to calculate P total. We know our N total because we just calculated it a moment ago. That is 0.712. Back here, we were told our volume was 1.55 liters. And our temperature was 18 degrees Celsius. To be able to use this calculation, I need an R, which is 0.0821 atmosphere liters per mole Kelvin. You got to make your units match. So I've got to change this temperature unit into Kelvin. Which is 291.15 Kelvin. All of my other units are matching. So then I just need to rearrange this equation by dividing both sides through by V. So it's going to be P total equals N total RT divided by V. So P total equals 0.712 moles times 0.0821 atmosphere liters per mole Kelvin times 291.15 Kelvin, all over our volume of 1.55 liters. And that gives us, did I calculate? Oops. That gives us a pressure of 1.1 atmospheres. I wanted to introduce this concept of mole fraction because you may see it in your Chem 101. But that is all of the new information. So now I will answer questions if you have them. Otherwise, I will see you Monday. If not, talk to you on Sunday.